So today we're going to talk about something called noble gas configurations. Noble gas configurations are basically just an abbreviated way to write electron configurations. So to start off, what I want you to do is go ahead and write the electron configuration for strontium and go ahead and write the electron configuration for krypton. Okay? So go ahead and pause the video, try that on your paper, and when you come back I'll have it written out. Alright, so there I have the electron configurations for strontium and krypton written out. So these are both fairly long, so it took a little time on your part likely. Krypton has 36 electrons, strontium has 38 electrons. So if you notice, for strontium and krypton, the first 36 electrons occupy the same orbitals, so they're exactly the same. So when writing noble gas configurations, we take a little shortcut to exploit this. So I can write strontium as brackets krypton 5s2. So what this means is that the configuration for strontium is the electron configuration for krypton plus a 5s2 orbital, which we see that is true up here. All strontium is krypton plus 5s2. So there's a couple of rules we have to follow when using this shortcut. We only put the noble gases in brackets, okay, because they have a full p orbital, so we only use them as our basis. We'll never really use helium, okay, it's so small we won't necessarily need to use that. So let's look at a few examples of how I go about this. So let's look at chlorine, for example. So let's say I wanted to write the noble gas configuration for chlorine. So the first step is, after you determine what element you're going to write the configuration for, you go up one row and find the noble gas. Okay? So then I put neon in brackets. Okay, so these are the noble gases: helium, neon, argon, krypton, xenon, radon in the far right column. So we go up a row, find the noble gas. We can't use argon because argon has more electrons than chlorine to start with, so that won't really help us. So we're going to start off with neon as the basis for our chlorine configuration here. So chlorine has a total of 17 electrons, but I already represented 10 of those right here because the configuration for neon would already have 10 electrons. So now I go back and use the little trick you learned in the last video. Let's see what neon ends with. So the configuration for neon ends in 2p6. So if I were to go up here and write out neon, it would end in 2p6. So if I look at the Aufbau diagram, I find 2p6, and I want to start with what comes right after that. So neon includes 2p6. After 2p6, we have 3s2. After 3s2 comes 3p. P can hold 6 electrons, but only needed to add 7 more because chlorine has 17 electrons, neon already had 10, so I can put 2p5. So this really is the same thing as writing out the whole electron configuration for chlorine. It just saves us a little bit of work here, okay? It's a few less steps. So let's look at the noble gas configuration for, let's just say, barium. Okay? So barium, if we look at it on the periodic table, has 56 electrons, so that would take us quite a while to write out. But if I use the noble gas configuration method, let me back up, I haven't said this yet. Most of the time we're only concerned with the last few pieces of the electron configuration, the last few electrons, the outermost electrons. Those are the electrons that are most reactive. They're the ones where chemistry happens. So we really don't care about the first 85% of them. We care about the last few little pieces. Those are the valence electrons that are reactive. So I said barium, I got off topic. So we find barium, we go up a row and find xenon. So xenon is going to be the base for our noble gas configuration. Okay, so a couple things we have to figure out. Barium has 56 electrons. Xenon accounts for 54 of those. So this little piece right here already accounts for 54 electrons. I only have to deal with 2 more now. So I see that xenon ends in 5p6. So I go find 5p on my Aufbau diagram. After 5p comes 6s. Okay? So now I can just add 6s2 and I'm all done. we can go back and check ourselves now. Should barium end in 6s2? Yes, based on the rules, we know that's correct. Okay. So that took me less than a minute likely, whereas the whole configuration for barium would have taken a long time. Okay, so it's just a little shortcut to help you to save you some time when writing these configurations. The one mistake people always make is they forget to go up one row to select the noble gas. Okay, so you can't choose the noble gas on that row because it actually always will have more electrons than the element you're trying to deal with. Okay, so one other thing I want to discuss in this video before we move on. Let's look at the configurations of sodium with a +1 charge, fluorine with a -1 charge, and then neon. Okay? So we remember if an element has a charge, the only thing that changes is we have to use that charge to find our new number of electrons. So sodium starts off with 11 electrons if it's neutral, but it's a +1 charge. I plug in the formula. I see that sodium +1 has 10 electrons. Fluorine starts off with 9 electrons. It gains 1 to gain a -1 charge, so it has 10 electrons. Neon has 10 electrons and it's neutral. Okay, so it's the same. So if I were to write out these configurations, I would say 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. Okay? So they're all the exact same. So electronically, all these have in terms of electrons, use a better word for that, they're all exactly the same. Okay? Their nuclei are still different. They have different numbers of protons and neutrons, but as far as their electron configurations go, there is no difference. So the term we use for this is isoelectronic. So two species that are isoelectronic have different nuclei, so they have different numbers of protons or neutrons, but they have the same electron configuration. Okay? So we'll find when we talk about charges in the future that a lot of atoms, or most atoms particularly, like to form charges that give them electron configurations of a noble gas. Okay, so if I gave you a list of charged species and a list of uncharged species and I asked you to find two that were isoelectronic with each other, all you'd have to do is find the number of electrons that each atom had and then find two that are equivalent there. So hopefully it wouldn't be too difficult at all. So just to review here, we really have three ways to represent the orientation of electrons in an atom. So the first way is the electron configuration. We'll call it the electron configuration notation. Okay, and that's where we write out the full 1s2, 2s2, 2p6. Then we have the noble gas configuration. And the noble gas configuration is nothing different. It's just an abbreviation or shortcut for the electron configuration notation. Then we have orbital notation. You remember orbital notation, it shows us the actual electrons within each orbital. So let's just look at the orbital configuration for chlorine, just to make sure we're on the same page here. So if I wrote out the full configuration for chlorine, the electron configuration, I would write 1s2, 2s2, 2p6, 3s2, 3p5. So that is the full electron configuration. The noble gas configuration for chlorine, we already did, is right up here. So the orbital notation for chlorine, I would do like this. 1s has one orbital. 2s has two orbitals. 2p has three orbitals. 3s has one orbital. 3p has three orbitals. Then I fill in with electrons. 1s has two. 2s has two. So 2p has 6 here. So if I don't do it correctly, nobody would ever know, but it's a good habit to follow the rules here and put 1 in each orbital before I go back and put the second electron in. 3s has 2 and 3p has 5. Okay. So that is the orbital notation for chlorine. So I could ask you, how many unpaired electrons does chlorine have? And based on this orbital notation, you could look and say, okay, chlorine has one unpaired electron. So in the future, when we start to discuss reactivity, we'll often look at the number of unpaired electrons that an element has.